2.3 Atomic Number. As alluded to in a discussion question in the previous section, scientists of the period had only a very approximate idea of how many units of charge resided in the nuclei of the various chemical elements. Although we now associate the number of units of nuclear charge with the element's position on the periodic table and call it the atomic number, they had no idea that such a relationship existed. Mendeleev's table just seemed like an organizational tool, not something with any necessary physical significance. And everything Mendeleev had done seemed equally valid if you turned the table upside down or reversed its left and right sides. So even if you wanted to number the elements sequentially with integers, there was an ambiguity as to how to do it. Mendeleev's original table was in fact upside down compared to the modern one. In the period immediately following the discovery of the nucleus, physicists only had rough estimates of the charges of the various nuclei. In the case of the very lightest nuclei, they simply found the maximum number of electrons they could strip off by various methods: chemical reactions, electric sparks, ultraviolet light, and so on. For example, they could easily strip off 1 or 2 electrons from helium, making He plus or He++. But nobody could make this type of helium, presumably because the nuclear charge of helium was only +2 electrons. Unfortunately, only a few of the lightest elements could be stripped completely, because the more electrons were stripped off, the greater the positive net charge remaining, and the more strongly the rest of the negatively charged electrons would be held on. The heavy elements' atomic numbers could only be roughly extrapolated from the light elements, where the atomic number was about half the atom's mass expressed in units of the mass of a hydrogen atom. Gold, for example, had a mass about 197 times that of hydrogen, so its atomic number was estimated to be half that, or somewhere around 100. We now know it to be 79. How did we finally find out? The riddle of the nuclear charge was at last successfully attacked using 2 different techniques, which gave consistent results. And here there's a nice picture of the atomic, or the periodic table. One set of experiments involving X-rays was performed by the young Henry Moseley, whose scientific brilliance was soon to be sacrificed in a battle between European imperialists over who would own the Dardanelles during that pointless conflict then known as the War to End All Wars, and now referred to as World War I. Since Moseley's analysis requires several concepts with which you are not yet familiar, we will instead describe the techniques used by James Chadwick at around the same time. An added bonus of describing Chadwick's experiments is that they presaged the important modern technique of studying collisions of subatomic particles. In grad school, I worked with a professor whose thesis advisor was Chadwick, and he related some interesting stories about the man. Chadwick was apparently a little nutty and a complete fanatic about science, to the extent that when he was held in a German prison camp during World War II, he managed to cajole his captors into allowing him to scrounge up parts from broken radios so that he could attempt to do physics experiments. Chadwick's experiments worked like this. Suppose you perform 2 Rutherford-type alpha scattering measurements, first one with a gold foil as a target as in Rutherford's original experiment, and then one with a copper foil. It is possible to get large angles of deflection in both cases, but as shown in the figure, the alpha particle must be heading almost straight for the copper nucleus to get the same angle of deflection that would have occurred with an alpha that was much farther off the mark. The gold nucleus charge is so much greater than the copper's that it exerts a strong force on the alpha particle even from far off. The situation is very much like that of a blindfolded person playing darts, just as it is impossible to aim an alpha particle at an individual nucleus in the target. The blindfolded person cannot really aim the darts. Achieving a very close encounter with the copper atom would be akin to hitting an inner circle on the dartboard. It's much more likely that one would have the luck to hit the outer circle, which covers a greater number of square inches. By analogy, if you measure the frequency with which alphas are scattered by copper at some particular angle, say between 19 and 20 degrees, and then perform the same measurement at the same angle with gold, you get a much higher percentage for gold than for copper. In fact, the numerical ratio of the two nuclei's charge can be derived from the same experimentally determined ratio. Using the standard notation Z for the atomic number, charge of the nucleus divided by E, the following equation can be proved. By making such measurements for targets constructed from all the elements, one can infer the ratios of all the atomic numbers, and since the atomic numbers of the light elements were already known, atomic numbers could be assigned to the entire periodic table. According to Moseley, the atomic numbers of gold, or copper, silver, and platinum were 29, 47, and 78, which corresponded well with their positions on the periodic table. Chadwick's figures for the same elements were 29.3, 46.3, and 77.4, with error bars of about plus or minus 1.5 times the fundamental charge. So the two experiments were in good agreement. The point here is absolutely not that you should be ready to plug numbers into the above equation for a homework or exam question. My overall goal in this chapter is to explain how we know what we know about atoms. An added bonus of describing Chadwick's experiment is that the approach is very similar to that used in modern particle physics experiments, and the ideas used in the analysis are closely related to the now ubiquitous concept of a cross-section. In the dartboard analogy, the cross-section would be the area of the circular ring you have to hit. The reasoning behind the invention of the term cross-section can be visualized as shown in the figure. In this language, Rutherford's invention of the planetary model came from his unexpected discovery that there was a non-zero cross-section for alpha scattering from gold at large angles, and Chadwick confirmed Moseley's determinations of the atomic numbers by measuring cross-sections for alpha scattering. And this is a separate anecdote that I'm not going to read, called Proof of the Relationship Between Atomic Number and Scattering, although it's included here. Just going to keep reading. As an example of modern use of scattering experiments and cross-section measurements, you may have heard of the recent experimental evidence of the existence of a particle called the top quark. Of the 12 subatomic particles currently believed to be the smallest constituents of matter, 6 form a family called the quarks, distinguished from the other 6 by the intense attractive force that make the quarks stick to each other. The other 6 consist of electrons plus 5 other, more exotic particles. The only 2 types of quarks found in naturally occurring matter are the up quark and down quark, which are what protons and neutrons are made of, but 4 other types were theoretically predicted to exist for a total of 6. The whimsical term quark comes from a line by James Joyce reading 3 quarks for Master Mark. Until recently, only 5 types of quarks had been proven to exist via experiments, and the 6th, the top quark, was only theorized. There was no hope of ever detecting a top quark directly, since it is radioactive and only exists for a zillionth of a second before evaporating. Instead, the researchers searching for it at the Fermi National Accelerator Laboratory near Chicago measured cross-sections for scattering of nuclei off of other nuclei. The experiment was much like those of Rutherford and Chadwick, except that the incoming nuclei had to be boosted to much higher speeds in a particle accelerator. The resulting encounter with a target nucleus was so violent that both nuclei were completely demolished. But, as Einstein proved, energy can be converted into matter, and the energy of the collision creates a spray of exotic radioactive particles, like the deadly shower of wood fragments produced by a cannonball in an old naval battle. Among those particles were some top quarks. The cross-sections being measured were the cross-sections for the production of certain combinations of these secondary particles. However different the details, the principle was the same as that employed at the turn of the century. You smash things together and look at the fragments that fly off to see what was inside them. The approach has been compared to shooting a clock with a rifle and then studying the pieces that fly off to figure out how the clock works. Discussion questions, and I'll read them in. Why does it make sense that, as shown in the figure, the trajectories that result in 19 degree and 20 degree scattering cross each other? Actually, I'll just leave the discussion questions because I'm not feeling like reading them.